Okay, today we begin the fundamental theorem of calculus. This is a huge theorem of calculus that we're going to use time and time again. It's a way of figuring out the exact area underneath a curve. So we're going to do that through integration and bounds. So if we're going to find the area underneath a curve on the closed interval from A to B, we are going to find the integral of this, the antiderivative. We're going to plug in B first, then we're going to subtract the antiderivative of the value A. Make much more sense once I do a problem. Basically, all you're going to do is you're going to integrate this, you're going to plug in B, and then you're going to go minus, you're going to plug in A, whatever you get for your integral. So the first thing I'm going to do to introduce this is just, it says use a graphing calculator, and you guys can go ahead and get out your graphing calculators. And all we're going to do is determine if the area underneath the curve is positive, negative, or zero. We're not going to compute the exact area. This is just to figure out if it's positive, negative, or zero. So if you would go ahead and graph on your graphing calculator the cosine of 0 or the cosine of x, you will find that your graph looks like this from 0 to pi. So from 0 to pi, it would go up at 1, it'd come down here, and then it'd finish at negative 1. So you'd be talking about the area underneath the curve here and here. Knowing what we know about cosines and sines, we know that these two areas to be exactly the same. This one above the curve is positive, and this below the curve is negative. So therefore, since these are the exact same areas, then we'd be taking, maybe this is 5 and this would be negative 5, and adding those together, we'd end up with a 0 for our area underneath that curve. This next picture, if you go ahead and graph it on your graphing calculator, you will see that it looks something along these lines. And we're talking about the area underneath the curve from negative 2. I've got this spread out a little too far, so let's see if I can fix this, make it look a little bit better, a little bit more like what the curve looks like. So it goes something like this. There we go. So we're going to talk about the area underneath the curve would be here. This would definitely be negative area. It's underneath the x-axis. And here we would have positive area, but we'd have a lot less positive area than we would negative area. Therefore, we know this answer would be negative. Alright, now we're going to actually use the fundamental theorem of calculus, and in order to do that, what we want to do is we want to integrate what is given here. So I'm going to integrate this first. So I'll have 6x to the third over 3 plus 2x to the second over 2 minus 3x. I don't need to put plus c's because I'm talking about a definite integral and we're going to be using bounds. We only put the plus c's on indefinite when we're not sure where we're taking the area to and from. This does reduce, so I'm going to go ahead and do this first. And I end up getting, this is my integral, and we're going to go from 1 to 7. Well, when I plug in, because what I'm supposed to do is I'm supposed to plug in b first, b and then minus a. So we're going to have 2, and then I have 7 cubed, plus 7 squared, minus 3 times 7. This is all my first integral with the 7 plugged in. Then minus, you're supposed to do the same thing. Take the integral and plug in 1. Then you just simply figure out what each of those numbers are. I would simply put it in my calculator and let it compute. I can do a few of these pretty quickly. 7 to the third power, I don't know what that is off the top of my head. I could put that in real quick. 7 times 7 times 7 would be 343 times 2 would be 686. So 686 plus 49 minus 21, and then we have 2 plus 1 minus 3. When you compute this to be, your final answer would be 714. Going on and using the fundamental theorem of calculus, what I'm going to be doing is first integrating this, but before I integrate it, I'm going to rewrite this. This really says the square root of 2, and this is x to the negative 1/2 dx. By writing it this way, I notice that I have a constant. I can bring it out front. And so now I just simply have x to the negative 1/2 dx. Much easier to take the integral of. So I've got the square root of 2, I'm just carrying that along. I'd have x to the 1/2 over 1/2. And remember, this is a definite integral, so we're using the bounds. So now what I really have is I have square root of 2, and then this would be 2 square root of x, and then I'm just going to be plugging in the 1 and the 8. So what that gives me is I have the square root of 2. I'd have, when I plug in the 8, I'd have 2 square root of 8 minus plug in the 1, I'd have 2. I can distribute this out. This gives me, oops, switch slides accidentally. This gives me 2 square root of 16 minus 2 square root of 2. 2 square root of 16 is 8 minus 2 square root of 2. This is as far as I'm going to take it. The next problem has an absolute value in it. It's going to be much easier to just graph the absolute value rather than trying to talk about it without the graph. I notice that this is factorable, so I'm going to go ahead and factor it to make it easier to graph. And when I graph this, now I know that it crosses at, or goes through 0 at 1 and 3. When I plug in 0, I'd have negative 1 times negative 3, so I'd be at a height of 3. When I plug in 2, I have 1, and then I have a negative 1, which would mean it's going down to negative 1. And then when I plug in the 4, I have 3 times the 1, which would be 3. So I have this V that looks like this. We're talking about area underneath the curve, so I'm going to be finding the area of these regions right here. Now we really could integrate this, and maybe I will go ahead and write out the integral of this just so you can see what it would look like. You'd say from 0 to 1, and then this would be a positive section. So you'd have the positive portion of this. Plus, from 1 to 3, however, this is really the negative section that goes below the curve, so you'd have the negative area. And then I'm forgetting my dx's. I should go back here and put those in there. Plus, from 3 to 4 of another positive section. I almost think this is more work than anything. If you're to compute this, you will get 4 as your answer. If you're to find all these areas and add them together, you will also get 4. So either way you do it is fine. This gives me x cubed over 3 plus 4x squared over 2 plus 3x. And then we can continue to get that each and every time. This would be from 0 to 1 minus, and I just brought that negative out front. I'd have x cubed over 3 minus 4x squared over 2 plus 3x from 1 to 3 plus, then I'd have it one more time, x cubed over 3 minus 4x squared over 2 plus 3x from 3 to 4. And then what we'll do is we'll just plug in all those values. I will tell you that on this first one, you get 1/3 minus 2 plus 3 minus, we end up getting, to be minus 0, 9 minus 18 plus 9. And I'm writing this out quickly only because of the time that I have left on this tape. So you will want to spend time looking at each of these numbers, but I'm writing them out for you. Plus this last part is 64 over 3 minus 32 plus 12, and then that's minus, and this is the whole thing here, I'm running out of space, 9 minus 18 plus 9. This does give you 4 as your answer. I've gone through this really quickly on the last video, so I just want to go back to it. When I plugged in 1, I got each of these values minus, well, I didn't get 0 in each one of those, so that's why I only had those 3 values. Minus, when I plugged in 3, I would have got 27 divided by 3, which is 9. When I plugged in 3 here, I got 36 divided by 2, which is 18, and then I plug in 3, I get 9. Minus, notice how I put these in brackets because I'm subtracting this whole thing as well. It's minus this whole quantity, so when you plug in 1, you have the same numbers that you got at the beginning. Plus, then when you plug in 4, you get 64 over 3. You plug in 4, you get 2 times 16, which is 32, and then you get 12. Minus, when you plug in 3, you end up with those same values you just got. And then when you figure out all those, you get 4. It is a lot easier just to find the area of this triangle, the area of this triangle, and the area of this triangle, and add them all together for a total of 4. The next part, you need to know a trig identity that you may have not talked about in some time, and that is this one. So in order to do this one, we need to be able to use this trig identity, and what we're going to do is we're going to rewrite this and replace the tangent squared x plus 1 with secant squared x. Then what I can do is say, well, what that really is 1 dx. So when I integrate 1, I end up with x, and then I'm going to be finding the integral from 0 to pi over 4. And so I plug in pi over 4, and I plug in 0 minus 0, and I get pi over 4. This is my last example for this day, and what it looks like is a fraction, and I know it's going to be much easier to integrate this once I've rewritten it as a negative exponent. So what I'm going to do is raise this by 1 and put it over that power, and then I'd be finding the definite integral from 1 to 2. This gives me negative 1 over x from 1 to 2. Well, I'll plug in 2 first, so I have negative 1/2 minus, then I'm going to plug in my 1, which is a negative 1 over 1, or a negative 1. So this ends up being positive 1/2 as my answer.